welcome to 2013's first episode of I Love Chemistry with me, Dr. Winchester. We're going to be working through some energetics today. So there's a little question underneath and the answers underneath. So just open the questions and just have a little read through that before you watch this video. Really, so you maybe have a go at the questions before you even have a watch of the video. Okay. But we're going to start off on question 1, part A, and we're going to work through most of question 1 and a couple of bits of question 2 as well, just so we've talked about the 3 main different bits of energetics. So question 1 starts off, it says propane gas in the tank, must be talking about some kind of tank, is used as a fuel in the factory. The equation for its combustion is this, so propane C3H8 goes to with 5O2, reacts to make 3 CO2 and 4 H2O, and it tells you the enthalpy change for this is minus 2,220 kilojoules for every mole. Okay? Calculate the amount of heat energy in kilojoules produced during the combustion of 30 kilograms of propane gas. Okay, so to do this question, we need to think, this is how many kilojoules are made for every 1 mole, so I need to know how much for 30 kilograms. So at the moment I don't have how many kilojoules per kilogram, it's kilojoules per mole, so I have to convert this to find out how many moles there are. So how many moles of propane gas are there? If I have the mass, I can do moles equals mass over mR to find out the moles. So moles of C3H8 equals the mass over its mR. The mass will always need to be in grams if we're using mR values that are in grams per mole. So it's going to be 30 times 1,000, so 30,000 grams. Very important, that step. Divided by the mR of propane. So you look at your periodic table to make sure you get it in the right accuracy. You want at least 3-4 significant figures. So 12.01 times 3 for the 3 carbons. Plus 8 hydrogens, and hydrogen is 1.01, so 8 times 1.01. Okay, so you do that on your calculator. So let's find out what the MR is first. It should just be 12.01 times 3 plus brackets 8 times 1.01 close brackets equals the MR of that should be 44.11. And we're going to divide 30,000 by. Okay, so 30,000 divided by answer is 680. So we have 680 mole. 680 moles, isn't it? Of course, because we've just worked out the moles of propane, so 680 moles. The question wants us to know how much energy is produced when we burn 30 kilograms of propane. So if this is how many moles, and this is how many kilojoules for every 1 mole, then we're going to have to times how many kilojoules we get out for 1 mole by how many moles we have. So energy produced equals 680 moles times 2,220 kilojoules per mole equals maths, some massive number, which is 1509861. So 1 million, basically 1.5 million-ish. Okay? So we want to put that to how many significant figures? 3 significant figures, because that's what we're given in the question. So 1,510,000 kilojoules. Okay. Now, normally you'd be worried a little bit if you got an answer as big as that for that many kilojoules. That's a huge amount of energy, isn't it? But then you read the question again and you think, well, actually 30 kilograms is a lot of propane gas. Propane is a good fuel, so it produces a lot of energy. So it's not the end of the world. It does kind of make sense. So that does look like it should be the right answer. Okay. Next question is a really common question. Explain what's meant by the term average bond enthalpy. Bond enthalpy is the amount of energy given out when you break 1 mole of a bond, or 1 mole of bonds. average because you have to average over lots of different compounds. Okay, and this should be kind of third point there. Let's just have a look. Defines the enthalpy change required to break a covalent bond with all species in the gaseous state. So the little third one that I forgot just there was that all species need to be in the gaseous state when you make them. Okay, so I think 3 marks, so you've got to have 3 different bits to your definition there. Okay. So we're going to use some average bond enthalpy data here to calculate a value for the mole enthalpy change for this reaction. Okay, remember it's average bond enthalpy because you know this. It might be harder to break this up in propane than it was to break it up in cyclohexane, for example. It might just be 2 different compounds, so it might be slightly different difficulties to break the bond. So they take an average over a range of compounds. That's why it's always average or mean bond enthalpy. So first thing, with any question like this, you need to draw out the equation, and what we're going to be doing is breaking lots of bonds, so we're moving up in energy because it's endothermic to break bonds. We have to give energy to break a bond, we're pulling things away from each other. So you start off nice and low down on your cycle, always have to make a cycle with these. We're going to draw it out because we need to know what bonds we do. So for C3H8, let's draw that out. 3 carbons, 8 hydrogens, and I know this seems a bit long, but you don't want to make any mistakes, and you'll really be understanding what's happening here. Plus 3 5O2, 1, 2, 3, 4, 5. O has double bonds, it's in group 6, so it needs another 2 electrons to kind of make itself have a nice 8 number of electrons, so it causes double bonds. Okay, these are going to 3 CO2, again C, double bond to oxygen, carbon needs 4 bonds around it, oxygen needs 2 bonds to it, so that's why it's CO2 like that, plus 4 H2O. H2O is a bent molecule, remember, bond angle of about 104.5 degrees because it's got 4 electron pairs around the oxygen and they repel each other to make it based on the tetrahedron. Lone pairs repel more, remember, so that's why this water is this bent shape, and we've got how many? 4 of them. Okay, so now we've done that. We're ready to make our cycle. We've got to break all the bonds to get to the same level where all the bonds are broken and the things are in the gaseous state, and then we're going to make the bonds again, so go against breaking them to find the final enthalpy change for this. Okay, so this is delta H for the reaction. We're going to break all the bonds first and then make the new bonds. So we're going to have a state up here which has all these atoms. Remember, they're going to be the same on both sides, it's a balanced equation. So you have 3 carbon atoms, 3 gaseous carbon atoms, 1, 2, 3, 4, 5, 6, 7, 8, and that makes sense with 4 times 2 as well. 8 hydrogen atoms, and then 1, 2, 10 oxygen atoms. You see I put with G just saying that there were gas there. So there's, on this side we've got to break 3 different kinds of bonds. We've got to break 5 oxygen-oxygen double bonds. So this energy change is going to be 5 times the oxygen-oxygen double bond, which is 496. Because the bond enthalpy is breaking the bonds, I don't need to put any minus or anything there. It's that value is bond enthalpy. What have we done if we've gone from bonds there to no bonds? So we've broken the bonds. So if you're going over the process, you need to have exactly the number there. You don't take negative here. Here, 2 carbon-carbon bonds, so 2 times 3, 4, 8. And 1, 2, 3, 4, 5, 6, 7, 8. 8 times carbon-hydrogen. Carbon-hydrogen is 4, 1, 2. Okay, notice how I'm counting the bonds. I'm not counting the atoms at all, I'm counting the bonds. Here, we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen to hydrogen bonds, so 8 times 4, 6, 3. So now Hess's law says that whichever way we go around the reaction, it doesn't matter as long as we start in the same place and finish in the same place. I want to know what this delta HR is. I want to know what the change from propane getting burned to form carbon dioxide and water is. So I'm going to go from here to here. So our start is this level and our finish is at this level. Now let's draw out what the equation should be then. So delta HR, that's one way of going from start to finish, so the delta HR, the delta H reaction, technically the delta enthalpy of combustion of propane, equals, so instead of going from here to here, what I could do is go from here to here, so break all the bonds, and then make the new bonds. So I could go from here to here to here. So we'd be going from here to here, so we're taking the positive of all these values. Because we're going with the arrow, we go positive, not meaning that these are positive values, these values are whatever they are, but I'm not going to swap the change, so the positive in that way. Okay, positive of, now big brackets, 2 times 3, 4, 8. Also the positive of this thing, so 8 times 4, 1, 2. Also the positive of this thing, so 5 times 4, 9, 6. Gone all the way up this way. This has broken these bonds, these bonds, and these bonds. Now we want to make these bonds and these bonds, so we need to go against these arrows, so we take the negative of this value and this value. So negative, brackets, 6 times 7, 4, 3. Negative, because we're going against the arrow, 8 times 4, 6, 3. Okay? We plug that into our calculator, and it should get us the right answer. So let's see if it does. So literally, all I do is I just plug it into the calculator using the brackets exactly how I've written them down. I don't do anything extra, anything less. I want to make sure that this all happens perfectly. So I go positive, open brackets, 2 times 3, 4, 8. Close brackets, positive, open brackets, 8 times 4, 1, 2. Close brackets, positive, open brackets, 5 times 4, 9, 6. Close brackets, negative, open brackets, 6 times 7, 4, 3. Close brackets, negative, open brackets, 8 times 4, 6, 3. Equals, moment of truth, minus 1690. So minus 1690 kilojoules per mole. Always remember what it's measured in. All of these values are kilojoules per mole, so the answer is going to be in kilojoules per mole. So the enthalpy of combustion of, which I've called delta HR, of propane is going to be minus 1690 kilojoules per mole. So minus means it's exothermic. That makes sense because if I'm burning it, propane, I know I'm going to give out a lot of energy on it. Okay. So it's going to be exothermic. So, next little question. Just a couple of little wordy question here. The value obtained in B2 is different from the standard molar enthalpy change of combustion of propane gas given in A. Give 2 reasons for this. One thing to always think about this is why is one that we've really calculated the value obtained in B1. What is B1? Let's go to 1A. B1, explain what is meant by the term average bond enthalpy. Okay, so why the average bond enthalpy is different from, what the question is, the standard molar enthalpy change of combustion of propane gas is different to the value obtained in B2. So the value obtained in B2 was using the mean bond enthalpies. It's different from the standard molar enthalpy of combustion of propane gas. Okay, so of the specific gas. One reason to always think of is, well, here we're talking about specifically propane, which has special types of carbon. It's got a carbon-carbon, these carbon-carbon bonds surrounded by the carbon-hydrogen bonds. It's a specific molecule. It's not an average of all the carbon bonds in the world. It's these specific ones. So when you're breaking the bonds and making the bonds, really you're doing more than just breaking and making average bonds in any compounds. You're breaking the bonds in this compound. So that's one reason. That's a common one to come up, is that you're using, it's a real compound with specific types, if you like, of carbon-carbon bond, or specific environments of the carbon-carbon bond compared to the average ones that they use in this bond density values. And another one is just, the other one's a tricky one to get. Just look at the equations very, very precisely. Here, we're making the following reaction is not quite the enthalpy of combustion, actually. It is burning 1 mole of propane to make carbon dioxide and water. So it is combusting completely in oxygen 1 mole of propane, but we're making water in the gaseous state. okay, which is formed in the gaseous state, but to get all the energy out of this, actually you would need to cool it down to make water in its standard state, which is a liquid. So water here is not in its standard state, it's a gas. Water is normally at 25 Celsius, a normal pressure, a liquid. So another thing is that we haven't really quite got the enthalpy of combustion exactly the same. Okay, so it's not quite the standard molar enthalpy change of combustion because it's not in standard conditions. Okay, so just another kind of little thing to think about there. So next we're going to go on to question 2, which is probably going to be on another video.